Welcome to the deep dive. Ready to untangle the math behind machine learning?
Always.
We've got Mathematics for Machine Learning, the textbook, as our guide. It's dense, I'll admit,
Yeah.
but we're going to break it down chapter by chapter, like your personal math decoder rings.
That's a good way to put it. The book is all about building that intuition, so we won't just know the formulas, but why they matter in machine learning.
Exactly. Speaking of approaches, how do the authors suggest we tackle this?
Well, they actually give you two options, kind of like choose your own adventure. You can go the classic route, cover to cover.
Right, the hero's journey.
Exactly. Or if you're feeling more strategic, jump around based on what you need at that moment.
I like the flexibility. So, chapter 2, linear algebra. I gotta admit, the idea of polynomials as vectors blew my mind a little.
Oh, it's definitely one of those wait, what moments.
For sure.
We think of polynomials as equations right, like x squared plus 2x plus 1. But the book shows us, visually too, in figure 2.1b, that they can be treated as vectors. The coefficients, those numbers, become components of the vector.
So it's like looking at the same thing, but from a totally different angle.
Exactly. And that's key for machine learning, because we're not just dealing with simple lines or planes anymore. We're talking about vector spaces.
And the book really emphasizes how vital those are.
Oh, absolutely. It's the foundation. Vector spaces let us organize and represent our data in a way that makes sense for machine learning algorithms.
Okay, give me a concrete example of that, because I'm still wrapping my head around it.
Sure. So think about tuples of real numbers. Equation 2.1 shows it nicely, like 1, 2, 3. Each number represents a different feature of our data point.
So like if we were looking at houses, each house could be a vector. And those numbers could be things like square footage, bedrooms, lot size.
Precisely. Each house becomes a point in this, well, you could call it housing price space.
Love that. Okay, so then the book introduces linear independence and basis vectors. Why are those the MVPs of vector spaces?
Because they are essential for dimensionality reduction. Think about it like this. You've got a huge file you need to compress, but without losing the important stuff.
Okay, I can see that.
That's what basis vectors do for data. They let us represent it more efficiently without losing crucial information.
Super useful when you're dealing with massive data sets.
Absolutely. And then chapter 2 touches on linear mappings and affine subspaces. These are the operations that let us transform and categorize data.
Okay, so going back to our housing price space, a linear mapping could, like, stretch or rotate that space.
Exactly. And an affine subspace. That could carve out a specific section, like all the houses within a certain price range.
I see. So these abstract concepts are actually the building blocks for how we manipulate data in machine learning. Makes sense. Onward to chapter 3 then, analytic geometry. My notes say this is where things get visual.
That's the one. This chapter brings those abstract ideas we just talked about from chapter 2 to life. We get to see how they work geometrically.
Nice. So what kind of visual magic happens here?
We meet inner products, which let us measure similarity and distance between data points. It's like having a ruler, but for data.
Okay, I'm intrigued. So if we want to find houses with similar features, inner products are our tool.
Exactly. And the book highlights that there are different ways to measure distance, each with different implications. Like, think of navigating a city. The Manhattan norm is like following the grid streets, while the Euclidean norm is the straight line distance as the crow flies.
So choosing the right distance metric is key. Depends on the problem in our data, I guess.
Absolutely. Then there's projections. The book uses orthogonal projections to illustrate how data can be broken down into components. Think of shining a light on something and analyzing its shadow.
I'm picturing it. So we're simplifying the data by looking at it from a different perspective.
Precisely. This is actually the basis for techniques like PCA, which we'll get to later.
It's like the authors are giving us these little hints, these building blocks, and then bam, powerful machine learning techniques later on. Love it. Chapter 4, matrix decompositions. Matrices still kind of intimidate me, but the book promises some deep insights here.
Ah, yes, matrices. They often get a bad rap as just grids of numbers.
Yeah, a bit overwhelming.
Right. But this chapter argues there's so much more. Think of it like taking apart a complex machine piece by piece to see how it all works. Matrices help us break down complex relationships in our data.
Okay, that analogy helps. So then we have determinants, which the book says tell us about the volume of the data.
Yes, and it uses some really great visuals, figures 4.2 and 4.3, to help us visualize that concept.
Visuals are always appreciated.
Absolutely, but the real stars here are eigenvectors and eigenvalues.
Those sound a bit intimidating. Why are they so important?
Because they reveal the hidden structure of data. Imagine them as detectives, highlighting the directions of greatest variance, like the backbone of the data cloud. The book even uses an example from biology, the neural network of C. elegans, a tiny worm.
Wow, so we're not just talking abstract numbers, we're talking about understanding biological systems.
Exactly. And you can actually see this in Figure 4.5. Pretty cool stuff.
Definitely. Okay, Chapter 4 also introduces different ways to decompose matrices, right?
It does. You've got Cholesky decomposition, singular value decomposition, SVD, and eigenvalue decomposition. Each one is like a specialized tool for simplifying different kinds of data problems, like choosing the right wrench for the job.
Gotcha. So matrices are much more versatile than I initially thought.
Yeah.
On to Chapter 5, vector calculus. I remember derivatives and gradients from college, but how does calculus apply to machine learning?
Well, this chapter gives us the tools to optimize machine learning models.
Hmm.
Think of it like fine-tuning your machine for peak performance.
And gradients are like the instruction manual for that fine-tuning.
Exactly. They tell us how to adjust our model to improve its accuracy. Imagine trying to reach the highest point on a mountain, the peak.
Okay, gotta love a good analogy.
Gradients point us uphill towards the summit.
Got it. So the steeper the gradient, the faster we're learning, moving toward the optimal solution.
Precisely. Now, the chapter also introduces the Jacobian and Hessian, which might sound scary, but they're really just ways to organize information about how our model's output changes. Think of them as, well, matrices of partial derivatives.
Okay, matrices again, but I'm starting to get a little more comfortable with them now.
That's great. And don't worry, the book has a nice visual breakdown of this in Figure 5.7. Visuals are always helpful.
For sure. Okay, so we've covered linear algebra, geometry, and calculus. I'm starting to see how these build on each other. What's next?
Next up is Chapter 6. We're entering the world of uncertainty, randomness, probability, and distributions. This is where machine learning gets really interesting.
Because real-world data is messy.
Exactly. It's not always neat and tidy like in textbooks. We have to deal with uncertainty. So this chapter gives us the tools to do that.
Okay, I'm ready to embrace the chaos. What are we talking about specifically?
We'll be diving into the basics. Discrete versus continuous probabilities, the famous Bayes theorem, and of course the Gaussian distribution.
Oh yes, the bell curve.
It pops up everywhere.
Why is that? Why are Gaussian distributions so popular in machine learning?
Well, first, they're mathematically friendly, relatively easy to work with. And second, they accurately model a lot of real-world phenomena.
Gotcha. The book actually has a nice visual comparison in Figure 6.8, showing one-dimensional and two-dimensional Gaussians.
That's a good one to check out.
I will. So we're using probability distributions to represent what our beliefs about the data, like how likely a house price is to fall within a certain range.
That's the idea. And then we have Bayes theorem, which is like our belief updating machine. We start with a prior belief, maybe based on expert knowledge or past data, and then we use new evidence to refine that belief.
So it's all about learning and adapting as we get more information,
Yep.
just like a good machine learning model should.
Precisely. And then there are conjugate priors, which are basically shortcuts and Bayesian calculations. They make things easier to compute.
Efficiency is always welcome.
Definitely. And Chapter 6 also introduces the grand unifying theory of probability distributions, the exponential family.
The what now? That sounds intense.
It might sound scary, but think of it like the Avengers of probability distributions. It brings together a whole bunch of common distributions, including our beloved Gaussian, provides a framework for understanding their properties and how they're related.
I see. So it's about finding elegance and simplicity amidst all the complexity.
That's a great way to put it.
Okay, on to Chapter 7. Continuous optimization. This is where we find the best solution out of a million possibilities, right?
That's it. Optimization is at the heart of machine learning. We want to find the perfect set of parameters for our model, the ones that minimize errors and make it perform the best it can.
And gradient descent is our trusty sidekick in this quest.
It is. Chapter 7 takes us deeper into gradient descent, exploring different variations: batch, mini-batch, stochastic.
So like different ways to navigate the terrain, all leading to the same peak.
Perfect analogy. Some paths are smoother, others are more rugged, but they all aim for the optimal solution.
I like that. Now, the chapter also talks about constrained optimization. That sounds like a real-world scenario where we have limitations.
It is. Imagine you're designing the best airplane possible, but you have constraints on weight and fuel efficiency.
Ah, yeah, trade-offs.
Exactly. Constraint optimization is about finding the best solution within those limitations. And the book introduces Lagrange multipliers, a mathematical tool to handle these constraints.
Okay, so we're learning to optimize, but in a way that reflects real-world limitations. What about convex optimization?
Yeah.
That sounds positive.
It is. Convex optimization problems are the mathematician's dream. We can reliably find the absolute best solution, the global optimum. It's like knowing that no matter which path you take, you'll always reach the highest peak.
That's reassuring. I like knowing that sometimes there's a guaranteed best solution. We've covered so much. Linear algebra, geometry, calculus, probability, optimization. Feels like we're building a powerful mental toolbox here. What's next?
Chapter 8, When Models Meet Data. This is where we connect all the mathematical foundations we've built to the practical world of machine learning.
Finally seeing how the theory translates into practice. I'm ready.
We'll be exploring different types of models, like parametric, non-parametric, and how they relate to different kinds of data.
Could you give me an example of that? Different types of models.
Sure. Let's say we're trying to predict house prices based on things like size and location. A parametric model, like linear regression, assumes a specific relationship between those features and the price. But a non-parametric model, like a decision tree, is more flexible.
So the model we choose depends on how complex the relationship is that we're trying to capture.
Exactly. And then we have model selection, which is about finding the Goldilocks model. Not too simple, not too complex, but just right for the task.
The Goldilocks model. I like that. Because a simple model might miss important nuances, and a complex one might overfit the data, just memorizing it without truly learning.
Precisely. And the book talks about techniques like cross-validation, which is basically testing out different models on a separate data set to see how well they generalize.
Okay, I'm feeling much more prepared to enter the world of models now. On to Chapter 9, Linear Regression. This rings a bell from stats class.
Linear regression, it's a classic for a reason. It's about modeling linear relationships between variables, like predicting a house's price based on its size. The book covers both the frequentist and Bayesian approaches to linear regression.
Could you remind me the difference between those? I always get them mixed up.
Sure. Frequentist statistics looks at the frequency of events, like how many heads you get when flipping a coin. Bayesian statistics takes into account prior beliefs and updates them as new data comes in.
So with the house example, frequentists would rely solely on the data, while Bayesian would start with maybe an expert's opinion and adjust it as we see more houses.
That's a great way to summarize it. And what's cool is the book connects linear regression back to concepts we've learned already. We see how vector calculus comes in for optimization, finding the best fit line, and Gaussian distributions are used to model the variability, the noise in our data.
It's all coming together. Chapter 10, Dimensionality Reduction with PCA. PCA comes up a lot with big data, right?
All the time. PCA is a game changer for simplifying high-dimensional data. Think images, text documents, anything with tons of features.
Right. So why is that simplification so important?
We'll try visualizing a data cloud in, say, 100 dimensions. Our brains just can't handle it. PCA lets us project that cloud onto a lower dimension, like 2D or 3D, where we can actually see the patterns.
So instead of a million features, we get the most important ones, the ones that capture the most variation. It's like finding the essence of the data.
Exactly. And the book ties this back to eigenvectors and eigenvalues, showing how those abstract ideas solve a real-world problem. Figure 10.6 really helps visualize the projection process.
Okay, so PCA is like finding the backbone of the data, those directions where things change the most. Then there's probabilistic PCA. What's that about?
Probabilistic PCA adds a bit more nuance. It lets us account for the noise in our data and deal with missing values in a more elegant way.
Makes it more robust.
Right.
I like it. We've covered a lot of ground, from basic math concepts to pretty powerful algorithms. What's next on our journey?
Chapter 11, Density Estimation. We're going to try to capture the essence of data using probability distributions. It's like trying to figure out the shape of the data, how likely we are to see certain values.
Okay, I'm visualizing data clouds with different shapes. So how do we capture those shapes?
The book focuses on Gaussian mixture models, or GMMs. They're really good at representing multimodal data.
Multimodal meaning data with multiple peaks or clusters.
Exactly. Imagine we're looking at customer data for an online store. We might find that customers cluster into different groups based on their buying habits.
Right, like the frequent shoppers versus the one-time buyers.
Yes. And a GMM can represent these groups as separate Gaussian distributions.
So we're creating a probabilistic model of our customers, with each Gaussian representing a different type of customer.
Precisely. And that model can be used for all sorts of things. Targeted marketing, personalized recommendations, really powerful stuff.
Wow, so we're not just looking at the data itself, but the underlying process that generated it.
That's a great insight.
All right, bring on chapter 12. This is one I've always been curious about, classification with support vector machines. SVMs, right?
Yes, SVMs are powerful tools for separating data into different categories. Think about sorting emails into spam or not spam, or identifying fraudulent transactions.
So it's all about drawing boundaries between different classes of
Yes.
data.
And SVMs are all about finding the optimal boundary, the one that maximizes the margin between the classes.
Margin being the space between the decision boundary and the data points. So wider margin means more confident classification.
You got it. And the book delves into all the mathematical details, from the primal and dual formulations to the kernel trick, which lets us deal with non-linearly separable data.
The kernel trick always sounds a bit magical to me. Like, we're warping space to make the data easier to separate.
It's a pretty powerful concept. We're essentially projecting the data into a higher dimension where a simple line can separate the classes.
Amazing. Okay, so we've got the basic idea of SVMs, but the book also mentions different ways to actually find this optimal boundary, right?
Absolutely. Remember those optimization techniques from Chapter 7? They come back into play here.
Yeah.
Methods like gradient descent and quadratic programming can be used to find the best SVM parameters.
So all the pieces are connecting. We've got the math foundations, the algorithms like PCA and SVMs, and now the optimization techniques to make them work in practice.
It's all interconnected. And the best part is that these concepts can be applied to so many real-world problems. It's like unlocking a whole new level of understanding.
This has been incredible.
Glad you're enjoying it.
I feel like we've barely scratched the surface, but in a really good way. I'm excited to dive deeper into these algorithms and see what else they can do.
Me too. And that's what we'll do in part 2 of our deep dive. Ready to see how this math actually works in the real world.
Oh, absolutely. That's what I'm most excited about. What you got?
All right, let's start with something we all use, recommendation systems.
Like how Netflix seems to know my guilty pleasure movies better than I do.
Exactly. And it's not magic, it's singular value decomposition, or SVD, which we talked about in Chapter 4.
Wait, so that matrix stuff can actually predict what movies I'd enjoy?
It can. Think of a giant matrix. Rows are users, columns are movies. Each cell is a rating, like 1 to 5 stars.
Okay, I'm picturing it.
Now, the catch is most of this matrix is empty, right?
Yeah.
Because people haven't rated every movie.
Right, that makes sense. So the challenge is filling in those blanks. How does SVD help?
SVD lets us break down that massive matrix into smaller ones that are easier to work with. These smaller matrices represent hidden patterns in the data, like genre preferences, director styles, even the mood of a movie.
So SVD is like a taste detective, uncovering the hidden reasons why people like certain movies.
I like that. And once we have those hidden patterns, we can use them to predict those missing ratings. We're basically finding users with similar taste and recommending movies they might like based on what other similar users enjoyed.
Okay, that makes sense. It's like saying, hey, you like these movies, you might like this one too, based on what people with similar taste have liked. It's amazing that matrix decomposition can do that.
It is pretty cool, and the book actually uses a movie recommendation example in Chapter 4, Section 4.6, to illustrate how this works. There's even a visual, Figure 4.10, showing the user movie matrix and the hidden patterns.
I'll definitely check that out. So that's one real-world example. Got another one, maybe from a different field.
Sure. PCA, or Principal Component Analysis, from Chapter 10, that's used all the time in image processing, like facial recognition and image compression.
PCA helps us reduce the number of dimensions, right? How does that work with images?
Well, think of a facial image. It can be represented as a vector of pixel values, but that vector could have thousands, even millions of dimensions.
Wow, that's a lot of data.
Right. PCA lets us find a smaller set of dimensions, called principal components, that capture most of the variation in facial features.
So instead of a million numbers to represent a face, we could use, say, a few hundred that capture the key info about eyes, nose, mouth, etc.
Exactly. And these principal components are like the eigenfaces of our data set. They represent the most common patterns in facial features.
Okay, I get it. So we can use these eigenfaces for face recognition then, comparing a new face to our database to see which one it most resembles.
Precisely. And PCA also helps with image compression. By using fewer principal components, we need less data to store and send images.
So it's a super efficient way to handle visual information thanks to linear algebra and eigenvectors. Pretty cool.
It is another great example of abstract math making a real difference.
Okay, feeling inspired to dive deeper into these algorithms and see what other problems they can solve. How about density estimation from chapter 11? How's that used in the real world?
Oh, density estimation. It's all about finding that hidden probability distribution that created our data, like figuring out the shape of the data, how likely we are to see certain values.
Right, right. We talked about Gaussian mixture models, or GMMs, being good at handling that, especially for multimodal data.
Exactly. If you're analyzing customer data, you might see different groups of customers based on their buying patterns, right? GMMs can represent those groups as separate Gaussian distributions.
So each Gaussian in the mixture is like a different type of customer.
That's the idea. And then we can use that model for things like targeted marketing, personalized recommendations.
So we're not just describing the data, but actually modeling the different types of customers within that data. Pretty cool. How about chapter 12? Support vector machines, or SVMs, always sounded kind of mysterious to me.
They do have a cool name, right? But in reality, they're workhorses in machine learning used for things like image classification and spam filtering. They're really good at drawing those boundaries between different classes of data.
So like deciding if an email is spam or not.
Exactly. They find the optimal hyperplane, remember, to separate the classes with the widest possible margin. The bigger the margin, the more confident we are in the classification.
It's like drawing a line in the sand, but with math. What about those cases where a straight line just won't work?
Ah, that's where the kernel trick comes in handy. It lets SVMs deal with non-linearly separable data. It's like projecting the data into a higher dimension where it becomes easier to separate.
I'm starting to understand the kernel trick a bit better. We're adding another dimension to our perspective so we can see patterns that weren't visible before.
That's a great way to think about it. And these examples, they really show how the theoretical stuff from the book has real-world impact.
This isn't just abstract math, it's the foundation for so many cool technologies.
Absolutely. And the applications are always expanding as the field grows.
Speaking of expanding, what other areas are using the math we've been talking about?
Well, we've touched on recommendation systems, image processing, even a bit of reinforcement learning. But let's talk about natural language processing, or NLP.
Ooh, NLP.
Right.
That's the world of chatbots, language translation, all that cool AI stuff that deals with language. How does the math from the book come into play there?
Remember how Chapter 2 emphasized vector spaces? Well, it turns out we can represent words, even whole documents, as vectors in a high-dimensional space.
Hold on, words as vectors. How does that even work?
One way is using word embeddings. Each word gets a vector based on how it appears with other words in a huge collection of text. Words that show up in similar contexts will have vectors that are close together.
So king and queen would have similar vectors, as would happy and joyful. We're capturing meaning using math.
Exactly. And once we have those word vectors, we can use linear algebra to do all sorts of things with text. Measure similarity, cluster documents by topic, even translate languages.
That's mind-blowing. The math we've been learning is powering some of the most advanced language technologies.
It really is. And the book's discussion of eigenvectors and eigenvalues in Chapter 4, that's relevant here too. Techniques like latent semantic analysis, or LSA, use SVD to extract the main topics or concepts from a bunch of documents.
It's like using math to understand the hidden meaning behind words. Okay, any other areas you want to touch on before we wrap up?
Let's talk about one more. Reinforcement learning. That's the field where AI agents learn to make decisions in complex environments.
That's the one with AI playing games or controlling robots, right?
Exactly. And a lot of the concepts from the book are essential for understanding how these algorithms work.
Really? Like what specifically?
Well, the discussion of gradients and optimization from Chapter 5, that's crucial for training these agents. They learn by trying things out, getting rewards or penalties. The goal is to find the best policy, the set of rules for making decisions that leads to the most rewards.
So we're using gradient descent to find the best way for the agent to win a game or navigate a maze.
You got it. And remember, Markov decision processes, or MDPs, from Chapter 6, they give us a way to model the agent's environment and its actions, even when there's uncertainty.
Right, MDPs were all about states, actions, transitions. How does probability fit into reinforcement learning?
Well, the book's discussion of probability distributions and Bayes' theorem, that's directly relevant here. A lot of reinforcement learning algorithms use Bayesian methods to estimate the value of different actions or plan future moves.
So it's like the AI agent is using probability to make smart choices, even when it doesn't know for sure what will happen.
Precisely. Reinforcement learning is a complex field, but the math from the book gives us a solid foundation to understand how it works.
This has been incredible. I'm starting to see that the math in this book isn't just theoretical, it's the engine behind some of the most exciting and rapidly developing areas of AI.
It's really cool to see how these ideas come to life in different applications, isn't it?
It is, and we've only just scratched the surface.
There's a whole universe of possibilities out there.
Well, on that note, I think it's time to take another pause and come back for our final part of this deep dive, where we'll wrap up our exploration of machine learning math. Wow, still processing all those applications from last time. It's mind-blowing how this math is shaping AI.
It really is. And this field, it just keeps evolving. The possibilities are expanding all the time.
So where do we go from here? What other mathematical adventures are waiting for us?
Well, we've covered a lot. Recommendation systems, image processing, natural language processing. We even touched on reinforcement learning. But there's another area I think we should talk about, the intersection of machine learning and healthcare. Well,
Healthcare. That's fascinating. I know there's a lot happening with AI in medical diagnosis, drug discovery. How does the math from our book fit into all of that?
it's used everywhere. But let's focus on one example, medical image analysis. Let's say we have a set of MRI scans,
Okay.
and we want to train an algorithm to detect tumors.
So using machine learning to help doctors make diagnoses.
Exactly. And, the math we've been learning, it plays a key role here. Remember PCA, principal component analysis from chapter 10.
PCA. Yeah, that was the one for reducing dimensions.
Right. And it's not just for faces. We can use it for medical images, too.
So instead of finding eigen faces, we're finding, what, eigen tumors.
Uh-huh. Yeah, you could
Yeah.
say that. PCA helps simplify that MRI data, highlighting the features that make tumors stand out from healthy tissue.
So it's like a filter, helping the algorithm focus on the most important differences.
That's a good way to think about it. And those support vector machines, or SVMs, from chapter 12, they're also used a lot in medical imaging.
For classifying tumors, right? Like malignant versus benign.
Exactly. SVMs can learn to classify different tumor types based on the features in those images, so it's giving doctors more information to make treatment decisions.
Wow, it's amazing how this math is literally being used to improve healthcare, even save lives. Any other healthcare applications that you find particularly cool?
Oh, absolutely. Drug discovery. Imagine having a huge database of chemical compounds, and you need to find the ones that might be effective against a specific disease.
Okay, so like finding a needle in a haystack.
Exactly. But with math as our guide, machine learning algorithms can analyze those compounds and predict which ones are most promising.
So it's all about analyzing relationships, chemical structure, biological activity, disease pathways.
Right. And all the math we've been talking about, regression, classification, clustering, those are all tools in that analysis.
This deep dive has been incredible. We've gone from basic math concepts to seeing how they're applied in all these amazing areas.
It's been a fun journey.
It really has. I feel like we just scratched the surface, but in a really good way.
I'm excited to keep exploring this world of machine learning.
That's great to hear. And remember, this field is constantly evolving, so there's always something new to learn.
And thanks to this deep dive, I feel much better equipped to learn it.
That's what we like to hear. Remember, the power of machine learning is in its ability to learn from data, to make predictions. And with a solid understanding of the math, you can really harness that power.
Well, thank you for being such a fantastic guide on this mathematical adventure.
It was my pleasure.
And to all our listeners, thank you for joining us on the deep dive. Keep that curiosity alive and keep exploring the amazing world of AI and machine learning.